I'm going to talk about monitoring for Flutter apps and how you can discover and fix every issue in your Flutter app. But before we start with the topic, a few words about myself. I'm a Google developer expert for Dart and Flutter. Right now I'm working for MediaMarkt Saturn, which is the largest e-commerce retailer here in Europe. In Italy, you might know it as MediaWorld. And I roughly started with Flutter when the first stable version was released. I'm also the author of a Flutter favorite package, which you can see here on the right side. And essentially what it does is it allows you to easily gather feedback from your customers or users. I'm also co-maintaining a couple of other libraries, like, for example, DIO, Sentry integration for GraphQL, and various libraries for working with Apple's parse-git format. Okay, now straight into the topic. So, you might know this. The user presses a button and nothing happens. Like, originally the counter should go up, but it doesn't work. That's typically because an exception gets thrown somewhere. I'll show you later how you can figure that out. That's the first part of this talk, and then in the second half, I'm going to talk about performance monitoring. And that's the issue where everything works, but it's slow. And mostly it starts with like one tiny bad review where someone says, well, it's slow. And then you get loads of them. And that's when you should start figuring out why is it slow. And it's usually pretty tricky because everything still works. But yeah, so where do you start to figure that one out? Okay, when should I start monitoring my application? With error monitoring, you should start pretty much at the start of your project. When you roll out the first version of an app, you're usually mostly occupied by putting out fires. So every edge case you didn't consider during testing and fixing bugs, crashes, and so on. Then later on, if the project is already a little bit ongoing, you figured out most of the issues that are crashing the app. And you're prioritizing and proactively solving issues, and you're building systems for faster debugging. But then you come to a time where the project is already long running, you have found product market fit, and you try to deliver the best possible experience. That's usually the time when you start investing in performance monitoring. And that leads to an overall improved quality because everything is as smooth as it should be. Okay, let's start with the catching exceptions and crashes part. We have multiple severities of issues. The lowest one is issues and exceptions you manually caught. So, for example, a try-catch block. Those are typically kind of expected because you wrote try-catch block. The next more severe issue are the uncaught and non-crashing issues. As you might know, if you run a Flutter application and an exception gets thrown that doesn't get caught, the app doesn't crash and quits like native Android or iOS apps. Instead, just nothing happens, which leads to a bad user experience. And then the most severe issue is uncaught and then crashing the app. That's not the case for Flutter web apps, but for mobile apps and also desktop Flutter apps. However, I'm not going to talk about these because that's mainly handled in native code, and that would be worthy of its own talk. Okay, so let's start with the uncaught and non-crashing exceptions. How do I handle these? And there are 3 ways of doing so. The first one is the so-called fluttererror.onError callback. This is where our beloved render overflow comes in when we have, overflowing widgets, with the yellow and black ribbon. And in order to handle or get notified for these issues, We first save the current handler, then we override it with our own handler. And then within that, we report the issue to a backend. And then we call the default handler again. We do that because usually people tend to override them themselves to do any special handling of it, and otherwise that would get lost. A pretty interesting fact about this is that this gets mostly called in debug mode for things like layout issues and so on. So during production, when the app is in the hands of your customers and users, you usually don't get a lot of errors by subscribing to this. The more important one is the default platform dispatcher .on error callback. And we already see a theme here. So again, we're saving the default and then override it ourselves, which is again pretty similar to the one before that. We report it to the backend and then call the default one. And then we have one more, which is only relevant for Flutter web apps. This is the rundown guarded method. And what it does is that it basically introduces another zone, a Dart zone, in which the code in the first callback is executed. On Dart.io platforms, that's what also the platform dispatcher error handler does. So this is really only relevant for Flutter web apps. And it should also only be used there. You could use it on Dart.io platforms, but you shouldn't because those introduce a slight performance overhead. And also Flutter is not made to be used in multiple Dart zones. So it's quite important to only run the Flutter Dart code within the first callback that's shown there. Otherwise, you run into all kinds of weird issues. And then again, we report the issue we might get to the backend. And what you've seen here in the last 3 slides is called instrumentation. Instrumentation is the process of adding code which collects exceptions and performance data. What we've done is manual instrumentation, and in contrast to that, automatic instrumentation is the process of automatically adding, subscribing to those issues. And that's typically done via reflection in other frameworks and languages, because in Dart we don't have that. Instead, we mostly rely on dependency injection or do it in setup code. So after we are getting notified for all these various exceptions that are uncaught, we want to increase our debuggability and actionability for those issues. We do that by, for example, adding the app version, the Dart and Flutter version, device information, and whatever is helpful for us as metadata to those exceptions. We could do that ourselves by using the platform package info plus package, the device info package, and so on. But writing all of this is quite tedious, and honestly, no one of us kind of wants to do it themselves. So instead, we can use ready-made services. Those are 3 very popular ones. There are way more. That's also available for Flutter. But let's take a look at what those offer briefly. So to my knowledge, Sentry is the one service which supports all platforms where Flutter runs. No other service does it. And it's also quite easy to set up. I show that in a second. It has a lot of additional packages, and it can be self-hosted for free, so that's quite awesome. Then we also have Firebase, Crashlytics, and Performance, which is free, but it also only supports iOS, macOS, and Android. So if you're looking for something for desktop platforms, it might not fit your needs. Also, the setup code has to be done all on your own. So the sites I've shown before is what you would have to do yourself for Firebase. Then there's also Datadog, which is very expensive, I've heard. But it supports also web in contrast to Firebase and iOS and Android. And it's really easy to set up and also has lots of additional packages to make things easier. What's important when comparing services for error monitoring is that you just use one at a time, because using multiple might lead to data losses, because they all listen to these same callbacks, and then they might interfere with each other. So it's important to evaluate one after them. Okay, so this is how you initialize Sentry. Essentially, you just call Sentry flutter.init. Then you set up the DSN, which is the connection to the project on their website. And then we have the app runner callback in which you run your application. This gets internally passed to the run don't guarded callback. So this works for web applications, but if you don't deal with web applications, you can just call Sentry like this. Okay, so this is then how you manually report an exception to Sentry. Pretty simple, and it works also for the other services virtually identical like this. Instead of Sentry, it's then Firebase Crashlytics or Datadog.capture exception, or kind of similar to that. And then after we've done that, we want to see our exceptions that we observe during the production use of our application. And then in Sentry, it might look like this. So we have lots of information, these stack trays, and then at the bottom, there would be a lot of logs that lead to this exception. On Crashlytics and Datadog, it looks somewhat similar. It's mostly the same information, just looks a little bit different. And as seen here, we get lots of information that ideally help us to easily fix the issue. So we can see on which operating system the exception has been thrown, in case it might be specific to a certain operating system. Okay, that was the easy part of this talk, and now we're coming to the distributed performance tracing, which in my opinion is way more interesting. Okay, you might remember those loads of bad reviews. I thought of an example, which is the weather app. I promise I didn't copy that from Andrew this morning. Yeah, and it essentially consists of two parts. So on the left side, we have the mobile application, which talks to the GPS service in order to find a GPS log, which then gets sent to the backend. That backend gets the coordinates, looks up the upcoming weather data for the next few days in the database, reports that back to the application. So it's basically two parts of a distributed system. This is also why it's called distributed tracing. And now somewhere in this system, there's something that makes it go slow. But it still works, so we don't get any stack trace or any other hint that might lead us to a solution where we should start looking. So what do? We start looking at implementing distributed tracing, and when we implemented it, it looks something like this. This is a trace, and you might see a certain resemblance to the Dart performance dev tools, which also shows traces like this. Each of those rectangles is a span representing a certain operation. So, for example, the yellow rectangle represents how long it takes to get a GPS log. The rectangle below that represents the outgoing HTTP request, and so on. And each of those, so that's one trace, but it spans across two parts of the application, of the distributed system. So first is the application, which is the top part. And then in blue, we have the server part. And there's already one problem we can see. We have spans that are shown, that are recorded on the server part. And there are spans that are recorded on the application part. And then the problem is, how do we know which spans that are getting recorded on the app belong to the spans that are recorded on the server? And we do that with something that's, wait, no, I think I messed up. Okay, yeah. We do that with something that is called context propagation. That is the process of making the, well, other system, so, context propagation is the mechanism that makes the other part of the system aware of where the originally span came from. And it works actually quite easy for HTTP requests, because we can just add the relevant span IDs to the HTTP headers. And there's even an open format for that, known as the W3 trace context, which we can make use of. And we implement that on the app, so on the client side and on the server side. Okay, now that we know how we should do it in theory, we're taking a look at the code of how it should work when we implement it. I'm using Sentry as an example, mostly because I'm familiar with it, but it works quite similar with every other service too. And as the backend part, I'm using Dartfrog because, well, we're here on a Flutter conference and Dartfrog uses Dart, so it's quite easy to understand. So again, we're starting with the app part, and we're initializing Sentry as seen before. But we're adding now an option which is called the traces sample rate. This enables performance tracing for Sentry. In contrast to exceptions, we're getting traces, or we're starting traces every time the operation we want to trace gets started. That means if we have a lot of users, we obviously also record a lot of traces. And if it's really like millions of users, that's a huge amount of data. Usually we don't need that much data, so we only record a percentage of that. And that's what the numeric value for the traces sample rate does. Basically says how many percent of the traces should actually be sent to the server. For debugging, it's usually you set 1 because you want to know every trace you're getting. But in production with a lot of users, it usually goes towards 0. So you only record like 1 or 2% of all traces. Then for the material app, we're adding the Sentry Navigator Observer, which is responsible for starting our root transaction, which is the red rectangle we've seen previously. And then the next part is using the Sentry HTTP client, which actually makes the context propagation happening. And it also starts the HTTP trace. That's also available from Sentry for DIO, so you can use whatever you want. And then lastly, we do some manual instrumentation for the GPS log to figure out how long that takes. First, we're looking up whether there's a current active span, and then starting a child for that. We're wrapping the getting of the current location on a try-catch because we also want to know how many of those traces are successful or not successful. So we set that in the catch block in case an exception occurs, but we don't really care about the exception, so we just rethrow it. In the finally block, we're finishing the span, which, well, finishes the span in every case, of course. So that's what we have to do in the app. Now going to the backend with Dartfrog. There we are just adding the Sentry Dartfrog package, which enables Sentry for, well, Dartfrog. And again, we are starting by initializing Sentry, setting the sample rate. Here, of course, again, the same applies. In production, we don't really want to record every trace, only a few, depending on how many users we have. Then we're adding a middleware, which is the Sentry middleware. You might know that from, for example, DIO or other web frameworks. The middleware essentially gets run before and after the endpoint gets hit, or your code for the endpoint gets run, and then does some additional logic. The Sentry middleware in particular then reads the HTTP headers in order to start the spans and traces from the app, which then does the context propagation on the backend side. And that's actually already it for instrumenting the backend. And then we have the whole system set up, and we can start looking at the completed traces on the backend. That then looks something like this. It's like, again, a flame chart where we can see how long certain operations took. In this particular example, the HTTP spans for the backend and app were combined, so it's not that many spans we're seeing. But now we can see actually there's a huge nothing between the start of the HTTP span and the start of the database span. And that indicates that that's the part where we're getting slow. And now we know where we should start investigating and how to fix the slowness of our application. Thank you. That's already it. Yeah, that was awesome.